have, if you look at this over here, there's absolutely no intercept. The intercept is 0, so it's not RT plus C. And that essentially, the function is also equal to limit P approaching 0 PV bar. So if I just remove that limit part and I tell myself in the back of my mind that look, pressure is going to be low, so let's keep this limit part out of the paper, but definitely in the mind. So I have this nice looking equation, which I'm sure you're all familiar with, is the ideal gas equation, right? It of course comes from the the earlier definitions of Boyle's law or Charles' law, or the other way around maybe. The Boyle's law and the Charles' law are all inbuilt into this equation. You keep the temperature constant and you see that PV is a constant, which is the Boyle's law. You keep the pressure constant and you see you get the Charles' law back. So what's it based on? It's based on some assumptions. Yeah, assumptions. And assumptions make everything horrible. Well, they give you a simple looking picture, but they really mess up the entire science. But then that's where you start with, right? Start with the assumptions, get things wrong, do some corrections to that, and then try to improve your model. So the assumption is low P, low pressure, which essentially gives you large volume, which is also related to the fact that a high temperature should be there. Now, if you have a low pressure or a large volume and a high temperature, then this ideal gas equation is quite valid, or maybe very close to being true. Not exactly true, but very close to being true. That's what I would say. But what exactly does it? Well, the assumptions now. The assumptions are that, look, the ideal gas equation essentially says that these gas molecules, or whatever these were at that point of time, these gas molecules are one thing, not interacting with each other, not non-interacting, right? And also that these gas molecules are essentially point particles, so they do not have any volume, no volume. You see, if you think about large volume of the gas itself, so this is about the molecules. So if you think of this large volume of the gas, then the small gas molecules volumes can be ignored. If you think of low pressure and large volumes, yeah, or high temperatures, it's exactly simulating the same situation. These gas molecules would be very, very far apart. It's a very dilute gas, right? It's all vacuum inside. And these molecules are really far apart, separated, which also ensures that they do not interact with each other. So that is it. You have low pressures, large volumes, high temperatures. These are the regions where you could perhaps be happy with the ideal gas equations, but for all practical purposes, you need to worry about the various pressure, volume, temperature conditions, and that's where you need to worry about these interactions, right? You need to worry about these interactions, and that comes about if you happen to look at the compression factor. So the compression factor Z is just defined as pressure volume by RT. Now pressure volume by RT should be essentially equal to 1 if it's an ideal gas, right? Or P by RT should be equal to 1 by volume of the ideal gas, molar volume of the ideal gas. So this is essentially equal to V bar upon V bar if the gas was ideal. So at low pressures, we've already seen that it behaves more or less like an ideal gas. So at low pressures, Z should be approximately equal to 1. But at high pressures, so if I pressurize the gas, then these molecules start coming together, they come closer, and they come even closer, and then they don't like each other when you start to come close enough. Yeah, too close for comfort, and then they start to repel. Yeah, once they start to repel, which means that the volume, the actual volume, would be larger than the ideal gas volume because they have repelled. So in that case, Z would be greater than 1. And when you do not have such high pressures, you have some intermediate pressures. Yeah. In that case, these molecules are not so far apart, but they do feel some force. Yeah. And that particular force usually is the attractive force. Usually. So when Z is less than 1 at the intermediate pressures, it implies that your attractive forces are dominant. Okay. You could use the virial expansion. It's given in your notes. So just you could go through these. And so let's just take that. So for example, I could expand this, right? Z or the PV bar is equal to RT into 1 plus B prime, let's say P plus C prime P square plus, and since all these expansions, the next higher order terms, they are low and low, and since you're not very far away from a low pressure, you're okay. The pressure is high but not so high, so the first term would be the most dominant, right? Yeah. And the next terms would start to be less and less dominant, so they would not be required so much. So what the idea would be then is that if I ignore all these terms, yeah, let's put it like this. If I ignore all these terms, then I recover back the ideal gas equation, which is true at very, very low pressures. Yeah. Very low pressures, all these terms just go away. As I keep on increasing the pressures, I would definitely require some of the terms to come in. Okay. So the more important thing is that not just seeing this compression factor, but the derivative of the compression factor. And there's a lot of properties we'll see later that depend on the derivative of this compression factor, dz by dp, which comes out to be B prime plus C prime P plus so on and so forth. Okay, 2C prime P. And if I'm interested in still in low pressures, right, what exactly is happening, then as P approaches 0, I just can cross out everything else. So dz by dp